Good morning, and thank you for joining today's session. So today we're starting a new unit, which is advanced database practice. So this is a level 5 qualification, and this unit award our learners with a total of 15 credit, which will count towards the achievement of this qualification. So the unit grading structure is with the pass, merit, and distinction based on the tasks that are required to do and the task that the learner will cover during the assignment. So for this unit, we have three sessions followed by our assignment discussion. And the unit aim for this for the advanced database practice is that with this unit, we'll teach the learner relational theory concepts such as normalization, foreign keys, ensuring consistency, tree-value logic, indexes for efficiency, database optimization. As an advanced course, it will presume that the learner have some familiarity with basic SQL extraction and manipulation techniques, such as those taught in our level 4 unit 8. So this unit will teach how to create various database objects and the benefit, such as tables, dynamic materialized views, triggers, stored procedures, user-defined functions. So let's now get into our presentation.
Victor, can I quickly interject a second? So I was talking with Sanor. I'm probably pronouncing his name badly. But my understanding was they because I don't know if you've seen, but on Moodle they've now put like basically they've put like the lessons which I think they must have set up through some sort of form of AI, but the sessions like the lesson criteria content is sort of like displayed in those videos. And I've watched the videos, I've gone through and watched them because they originally messaged me to ask. Let me just get the message up on my phone. Where is it? So yeah, they came to me and they said, "Oh, hi Johnny, hope you're well. Just checking if you require tutorials or lesson learning outcome-wise sessions." And I was like, "What's the difference?" Because I wasn't sure what the difference was. And they said the tutorial are the summary of the entire unit, providing gist essentially. So I think that's like the assignment discussion that we usually do in the last session.
Yeah,
As we have now the video walkthroughs on the Moodle site that you would have seen. So that's the ones I'm talking about. Basically, these sessions they've now made into videos with, I don't know, some sort
yeah.
of AI sort of thing covering it. And they said essentially we would want you to go through those and then discuss further queries in the tutorial for the unit with the tutor. So like the end, like assignment discussion. So
Okay. I was
yeah.
not told about that.
Yeah, that's all right.
But
Um,
probably they
so
set
I
up
just
in a
just
group
thought because
chat.
my understanding was that yeah that we would be going through like the last thing today, and not like session one this time, then session two, then session three. So I just thought
Okay,
I'd tell you because otherwise we'll end up doing the whole thing, which I'm
okay.
happy to do. But I thought
Yeah.
means you only have to do the one session instead of four.
Oh, wow, I was not aware of this. They probably said in some group chat maybe, and I missed that. I don't know.
Well, they messaged me that directly outside of the session group chat. Because usually I like when it comes to setting up, sessions for the next unit and stuff, I usually have Jill that I correspond with, but Jill was off, and it was assuming going from the level 5 group discussion, it was Sukhnor, Sukhnor. I think I'm pronouncing that right, Sukhnor. Um, so yeah, that's what they said in the private one-to-one WhatsApp with me, which is the one I usually use when I discuss with Jill about booking in the sessions. So yeah, that's what they told me, and that's sort of what I was expecting. I'm happy to go through the lessons in the same way that we normally would, but I just
Yeah,
wanted you to know because yeah, saves
yeah,
you doing.
I'll probably have to discuss with them because they sent me all the presentation, but
Yeah.
now you're saying that it's just assignment discussion, so no.
Yeah. Well, I'm happy to go through the first session today, and then we can always book the assignment discussion in uh for next week or something.
Yeah,
Yeah. Because that's how it reads to me anyway. That's what it sounds like they're saying.
yeah, I'm reading through everything. I can't find any message where they said that.
Let me see if because I've got you in WhatsApp, don't I? So let me just quickly uh wait a minute, let me see. Can I zoom that out a bit? Not really. Oh, actually I can get that. Right, and then let's find you because I know I've got you on here somewhere. Oh, actually, do you know what? I'll just go into our level 5 discussion group because you're in here, aren't you? Vic, there you are. Let me message you. Oh. Sorry, my phone's going a bit crazy. No, I don't want to do that. I want to. Oh, it'd be good if there was like some way to like, I don't know, like copy and paste this. Oh, there is. Copy. And then go to here. So if you have your WhatsApp ready,
Yeah,
Bosh, just sent you a screenshot I've just taken from my phone. And you can see like the UK Varsity business account has come from.
okay, yeah, I got it. Just checking if what tutorial. Okay. Mhm. I read that, but I was not being told.
Yeah,
They always say, "Are you available for session?"
yeah.
Give them availability, but they never mention that they're now using AI walkthrough for each tutorial.
Well,
Yeah,
let's go through the lesson 1 outcome because it'd be useful to go over it again anyway. Because actually, I think these are more in depth than the other videos. The other videos are only like 10, 15 minutes long each. So these are a bit more in depth. So let's go through this one and then we can always book the assignment one in like for next week if that's the way they want us to do it, or we can just continue to do it like this. I don't mind either way. I think this works better, to be honest. But
yeah. Okay, yeah. Yeah, just mention it to them though. This works
it's
better.
whatever fits best for you, really.
Yeah. Yeah, then they will now schedule the session.
Yeah.
Otherwise, I don't know. Okay. Do you
So
have
yeah,
any?
let's carry on.
Okay. Okay. So, with our first learning outcome, we're now going to understand advanced relational database concept. So we've already spoke about the unit aim, what we're trying to achieve with this learning outcome, what are going to be our goals. So some of the indicative content that we'll be covering in today's session is that we're going to look into SQL, SQL database and non-SQL. Then we'll now look into defining what a relational database, what type of relational database are available. So as we can see here, we have a definition for this, where relational database recap, where we can see that before diving into advanced concept, it is very important to understand that the basics, such as what a relational database does, how it stores data into tables, each tables and rows with the records and attributes, and also what these tables are connected, how are they communicating, how are they connected with each other, with primary keys and foreign keys. Then we'll look into advanced data modeling, where at an advanced level, we have data modeling, which includes ERD, entity relationship diagrams. And also we're going to look into normalization, why we now also have basic normalization with the use of 3NF, which removes redundancy and improves integrity. And also it is useful for advanced practice, which will include voice code normal form, which handles anomalies left from our 3NF. Also, we look into denormalization, which sometimes is used deliberately in performance tuning. And also we'll introduce redundancy to improve read speed. We also have complex relationship, where again from our ERD we'll understand our type of relationship. For example, we have many-to-many relationship using junction table, recursive relationship, for example, employees, managers, and other employees. Compositive keys, such as multi-column primary keys, surrogate keys, which are non-natural keys, auto-implemented integers, and UUIDs. Referential integrity enforcement using constants. Then we also have advanced SQL concept, where we look into proficiency in advanced relational database, also means knowing advanced SQL, such as joins, subqueries, common table, expressions, views, stored procedures and functions, and triggers. Also, we'll look into transaction and ACID properties, such as advanced database operations, which rely on transaction, which are automatic unit of work, atomism, all or nothing, consistency, where we look into valid state before and after, isolation, where we look into transaction that don't interfere, durability, which once is committed, changes survive any type of failure, concurrency and locking, where in a multi-user environment, database handle current access through locking mechanism. Delock and the resolution, deadlock and the resolution, isolation levels, where we're now looking into read uncommitted. Also, we're going to read commit the committed and repeatable read, and serializable. We're also looking into index and performance tuning, where we're now going to improve our query performance. So indexes are created on column frequently used with our where, join, or order by clauses. Use of clustered and non-clustered indexes. Understanding execution plan and query optimization techniques. Also, we have security and access control, where with advanced relational database management implementation, we're now going to include role-based access control, privilege and grant from read, write, execute, encryption, and auditing and logging of user activities. So with our learning outcome 1, we now going to discuss how SQL implement relational set of theory and relational models. So as we all know, when it comes to working with databases, we use
from Victor's MacBook Air.
We use SQL or SQL, which stands for Structured Query Language, and this essentially applies concepts that come from relational set theory and relational models. So these two ideas form the foundation of how relational databases are constructed and how they produce data. So relational set theory, we know that with the set theory is all about dealing with collection of distinctive elements. So in the database, those elements are rows, also called tuples, and they exist in tables which are equivalent to mathematical sets. So with SQL, uses this logic to manipulate and retrieve data. So for example, SQL will now support several set of operations that come directly from set theories. So what are these set theories? We have union, which combines the results of two select statements and removes duplicates, and is just like a set of union in mathematics. So we have SQL, where we're going to now select the name from our customer, and we use this union function to select from supplier. Insert, which we know that this returns only row that appears in both results, and this is the mathematical intersection for it. Then we have except or minus in one system, which returns row in one result but not in the other one. So when it comes to relational model, we're now introducing them, which was introduced by Edgar F. Code, which defines how data should be logically stored in this model. So we know that data is structured in relation. Each relation is made up of our rows and attributes, rows and columns. Each table has primary keys and a unique identifier row. And then foreign keys are used to create relationship between tables. So we now know that SQL is the practical implementation of this model. When we define a table using SQL, we're now creating a relation. So the SQL query logic and set-based thinking. So we know that another way SQL aligns with relational theory is in how it treats query and declaration of intent, not procedures. So when we now run a select statement, we now don't tell the system how to get data, as we just described the result set that we want. So with the select function, we know that we want to retrieve specific rows and columns from our database, and we will now use the select from and where function in order for us to retrieve the data. So now to summarize, SQL refers to principle of both the relational set theory and the relational model. By using set-based operation, union, intersect, and except, representing data in tables that act like sets, following strict rules about how data is stored, accessed, and related, applying mathematical logic to ensure data integrity and consistency. So now we're going to explain why SQL standard is not tuning complete and also what the consequences. So why SQL is not tuning complete? Standard SQL, as defined in the ANSI ISO specification, will now lack of key features required for tuning completeness, which include loops and recursion. So we know in the standard form, SQL does not have loop like while or for. It also doesn't support recursive logic unless explicitly extended. So some databases like Postgres support recursive CTA, but this is beyond the standards. So unbounded memory or states, for example, SQL operates on set of data with defined schema, which does not allow the creation of dynamic structures like linked list or trees that can grow indefinitely during execution. So no true conditional branching. Although SQL has case statement and some procedural execution, which offers if-else, these are limited in expressiveness and scope compared to the language like Python, Java, or C. So no variables or mutable states. For example, so basically you can declare variable or reassign values in pure SQL. These capabilities are usually provided by procedural execution. So consequences of SQL not being tuning complete. So with this limitation, which has both advantages and disadvantages, depending on the context. So what are the positive aspect of this? We can now have more predictability and safety. So because SQL is not tuning complete, it's easier for the database engine to optimize queries, estimate execution plan, and avoid indefinite loops. With performance tuning, is simpler, where queries are declarative and set-based. So if we now tell database what we want, not how to do it, this lets SQL engine apply its own optimization, which often result in fast performance. So with lower risk of runtime code, where we know that since SQL lack loops and embedded recursion, there's less chance of accidental writing a query that runs forever or consumes all resources. The negative aspect is that we now have limited algorithm logics where we can't implement complex business logics or algorithms like Fibonacci or advanced data manipulation. So directly in our standard SQL, so for these tasks, we now need to use stored procedures, functions, or external application languages. So with the dependence on extension, many real-world systems extend SQL to overcome its limitation. So for example, with T-SQL, we're now going to add procedural constructs. With PL SQL, such as Oracle, we're now going to add variables, loops, error handling. And with Postgres, we're now going to support recursive CTA and procedural language like PL or PGSQL. This means developers must learn vendor-specific features and risk losing portability between systems. So, not suitable for general purpose programming, where we can't use SQL to build entire applications. It only means that which only means that it's used for interacting with data, not for controlling flow, creating interfaces, or managing full program logic. So to summarize this, to put in simple words, SQL stands is not turning complete because of it was never designed to be. This is declarative language focused on querying and manipulating data, not building algorithms or controlling program flow. So now we're going to describe why data should be normalized and carried out normalization of table. So why data should be normalized? When it comes to design a relational database, one of the priorities is to have normalization, where it is the process of structuring data to reduce redundancy improve data integrity and make the system easier to maintain. So the benefit of normalization is that we're now going to eliminate redundancy, ensure that we have data integrity, improve maintainability, and support efficient queries. So here we have an example of how we can carry out normalization on tables. So let's see how we now have a single normalized table like this, where we have all the table. Then we have all our columns with our order ID, our customer name, customer phone number, product name, product price, and quantity. So we can now see that there are multiple issues here. Customer data is duplicated, product data is duplicated, difficult to update or delete customer or product cleanly. So our first step is to have our first normal form. So what we're doing with our first normal form, we're now going to remove repeated groups, ensure the atomic values in place. So our current table already uses atomic values, but we can improve our structure by separating repeating entities. Step 2, we're going to have a second normal form where we must be in first normal form and remove partial dependencies. So every non-key attribute must depend on the full primary key. So we now split this into multiple tables. So this is the whole process of normalization. So third normal form, so we must be in second normal form and remove transitive dependencies. So our non-key columns shouldn't depend on other non-key columns. So in this case, all non-keys attributes in each table are directly dependent on the primary key. So this structure is in a third normal form. What the benefit gained? So if John Smith changes his phone number, we only update this in customer. If the price of the laptop changes, we only update in product. And we can now analyze sales per customer or product without redundancies. And the data model is also clear, easy to maintain, and less prone to errors. So to summarize, we now know that normalizing data helps us building better, more scalable databases by reducing duplication, enforcing consistency, and organizing the structure for long-term reliability. In our merit activity, we're now going to compare the relational set operators. So what are our SQL operators? So we now know that when working with relational database, the underlying theory comes from relational algebra and set of theory, both of which describe operational sets. So SQL will now implement this operation in a more practical way, where we now compare the theoretical set of relational operators in the SQL counterparts. Set operators. So we now know that these come directly from mathematical set theory. So they work on complete result sets. These are union compatible, meaning they have the same number of columns and compatible data types. So we have set theory operators, SQL, equivalent, and the purpose. Relational operators. With this relational algebra also defines core operation for handling relations, such as a table. So SQL is going to map these to familiar commands. Relational joins. So joins are more advanced form of the Cartesian product with filtering applied. SQL has several join types that align with relational concepts. So the key difference between theory and SQL practice. So we have features, relational algebra, set theory, and SQL. So to conclude, we now know that relational algebra and set theory provides the formal mathematical foundation of relational databases, while SQL translate those concepts into practical commands. SQL doesn't follow them theory perfectly, especially when it comes to handling duplicates or no, but it still mirrors the logic closely through operators such as join, union, interselect, select, and where. Now we're going to evaluate the importance of ensuring ACID priorities and how it can be achieved. When we manage or design relational databases, we're now going to ensuring ACID properties which is fundamental to maintaining data integrity, consistency, and reliability. So these four properties, which are atomic, consistency, isolation, and durability, are essential for any system that performs transaction, especially when multiple users are reading from and writing to the same database. Atomicity. So this means that our transaction is treated as a single invisible unit. Either all the steps for the transaction are completed successfully or none of them are completed. Why does this matter? So let's say we now transferring money from one bank to another. The transaction now involves two steps: debiting one account and crediting another one. If only one step completes due to a crash of error, the database becomes inconsistent. With atomicity, this never happens and it's all or nothing. Consistency, we're now going to ensure that the transaction moves the database from one valid state to another, always presenting predefined rules such as control state and relationship. Isolation, we're now going to ensure that multiple current transactions do not interfere with each other. Each transaction must behave as if it's only one running. Durability, this means that one transaction is has committed the changes and is permanent even if there's a power failure or crash, or a crash immediately afterwards. So how can we achieve this? With our DBMS, we can achieve this ACID compliance through a range of mechanisms, most of which are built in, but this can be controlled or configured by developers or database administrators. So when it comes to transaction, we now use transaction, which goes with begin, commit, and rollback to group SQL operations together. This will now provide atomicity and the control point for success or failure. Constraint and triggers. This is to maintain consistency, and we can now define our primary and foreign keys, check constraint, trigger that enforce business rules at the database level, and this ensures that only valid data enters the system. Locking and isolation level. So to ensure isolation, our DBMS now uses locks, isolation levels like read uncommitted, read committed, repeatable read, and serializable. So we can now choose the right isolation level depending on how sensitive our data is to currency issues like dirty read, non-repeatable read, or phantom reads. Write-ahead login. So for durability, most databases use a write-ahead log before making any actual changes. It writes the changes to a log file if there's a crash. So the database management system can replay the log to restore committed states. Evaluation and real importance. So with our ACID properties, which aren't just theoretical, they will allow banking system and e-commerce platforms, airline booking system, and healthcare databases to operate reliably. Any system that handles critical transaction must enforce ACID. With that said, achieving our full ACID compliance can introduce performance overhead, high-speed distributed system like non-SQL databases. Some applications relax these guarantees, evaluate consistency instead of strict consistency. But in traditional databases system, the reliability ACID provide far outweigh the cost. To conclude, we know that with these properties, they now form the backbone of reliable, trustworthy database system, and also is going to be by enforcing atomic consistency, isolation, and durability. We can now be confident that even under failure, concurrency, or heavy load, our data will now remain accurate and secure. So whether we're writing transaction login or configuring isolation levels, understanding how to implement and maintain ACID is critical for any serious database application. So we have a case studies here where we're looking ACID versus base with the banking and retail system. So from the background, what is base? Well, we know that ACID is the gold standard for reliability and consistency in relational database. Base is an approach using non-SQL databases that focus on availability and scalability, particularly useful in distributed systems. So base stands for basically availability, soft state, and evaluating consistency. So base is often used in systems like Cassandra, MongoDB, Couchbase, and DynamoDB. So banking system, why ACID is critical for several aspects. For system requirement, so they have real-time financial transaction. Data accuracy must be 100. No tolerated for particular updates, and transaction must be atomic and recoverable. So example, we have money transfer. When we transfer £500 from an account to another, we're now deducting 500 from one account and adding into the other one. So both steps must happen together, not or not at all. If the system fails in between, we now have a particular completion, which will now cause financial loss or fraud. So how ACID support this? With atomicity, all steps have to be completed or not. Consistency, our account balance always reflect the current total. Isolation, if two people transfer money at the same time, this transaction will interfere. And durability, once committed, transaction is permanent even if the system crashes. So why base fails here? Base might allow account A to be debited into account B. Can debit before account B is credited, especially in high latency distributed setups. So it is important that we have eventually consistent, which is now acceptable for real-time financial system, with transaction control, which introduce risk of overdraft, double spending or incorrect balance. And then we have verdict, where banking system requires ACID and base is not suitable. With the retail system, where base may be acceptable. So these can be the system requirements is for high volume product category access, fast products search and order update, and it can tolerate temporary inconsistencies. Example for these are e-commerce flash sales. So during a flash sales with 1,000 users trying to buy a product, now base will now help us for stock count changes rapidly, some latency between inventory updates and what users see is unacceptable, and the system must stay available even on the massive lead. So how base support this? So basically available, the system will now respond quickly even if some nodes are out of sync. With our soft state, shopping cart data can be replicated across regions or updated later. Eventually consistency, if two users try to buy one last item at once. The system handles the conflict after the fact, while ACID might be limit this performance. So by locking the inventory row for every order, this can cause delay or timeout under heavy loads, ensuring strict consistency, which can slow the system and hurt the customer experience. And the verdict, where for large-scale, high-traffic retail platform-based providers, the scalability and performance needed, as long as eventual consistency is acceptable. So here, now in our table, we now have a technical summary between our relational database and our non-relational databases, where we have example for our use case, our consistent model availability, partition tolerance, transaction support, and latency. When it comes to the financial evaluation, we know that in mission critical system like banking, where accuracy is non-negotiable, ACID is essential. Even millisecond of inconsistency could lead to legal, financial, or reputational damage. So in retail system, especially global e-commerce or real-time product search, Base will now provide the flexibility and performance needed to serve thousands or millions of users. So with that said, many modern applications are now going to use a hybrid approach where they have ACID compliant databases like Postgres, Microsoft SQL Server, or Oracle for financial transaction, while Base compliant for non-SQL database. These are now applied for MongoDB or Cassandra for product search, caching, and login or analytics. So this was everything for today's session. Is there any question for me?
Thanks, Victor. No, that was all pretty clear. I used SQL in my previous job, obviously working in data analysis. It's typical common skill. I get to use it a little bit in my current job, my new job. But yeah, no, this all makes all pretty clear.
Oh, are you still working for I think it was a charity organization?
I'm working for a local authority now in data management. So
Oh, that was last year, right? No.
last year I was working in analytics,
Okay.
sort of like as a team leader in a sort of the charity sector, and now I'm in local authority.
Local authority. Oh, okay, that's good. Oh, well done for that.
Thank you.
Yeah. Yeah, okay. So I think I'll probably drop a message to Sunakor, I think, just to double check with them what they wanted to do with the sessions. And obviously, I think you might have to message them as well and let them know.
Yeah, that's fine. I'll message them.
Yeah.
No problem.
Yeah.
I'll put it in the level 5 group chat so that way like everyone can see it, and then
Yeah. Okay. I think it's best if you speak to them first, then they will let me know how you're gonna proceed with
how to
that.
proceed. No problem.
Okay, let's do that. Okay, thank you, Jonathan, and have a good rest of the weekend.
You too, Victor. Cheers for that. Take care.
All right, bye-bye.
Bye.